page, it talks about polynomials. It talks about the importance of our leading coefficient. And what I'm going to get you to do is to put a little note beside this. Because with our polynomial functions, we're going to separate them into two categories. One category that we're going to have is something called odd functions, and the other category is something called even functions. So odd functions, that's when your highest degree is odd. Makes kind of sense that way. And the thing that we're going to take away from odd functions is we're going to look at our most basic odd function, which is in a line, and we're going to say that the end behavior, and by end behavior we're going to say what happens at the end of a graph, the end behavior acts like a line. So what do I mean by that? Let's look back at our graphs. We have two odd functions here. We have an x cubed one, and if we're looking at the highest degree, it's odd. And if we look at the leading coefficient, it's a positive 1. What happens when you graph a positive line with the slope being positive? Does it go this way or does it go this way? Okay, it rises from left to right. So when you're looking at a positive line, it goes like that, right? And by the end behavior, it means it starts down here, it ends up there. That's what a positive line does. Notice our positive x cubed graph in B. It starts down here, it ends up here. It just has some woo in between. That's okay. But the end behavior acts like a line. If you took the end points and connected them, does it have a positive slope? Yes. So when I'm talking about the end behavior acting like a line, that's what I'm looking at. Just where does it start? Where does it end? It should be like a line. So with our negative x to the 5 graph, well, that's a negative odd function. What happens when you have a negative line? It goes down from left to right. And notice our x to the 5 graph here, that's where it started, that's where it ended. It's like a negative line. Starts at the top, ends at the bottom. Has a lot of crazy stuff go on in between, but that's how we know about its end behavior. And if we look at the most basic even function, right, that's where your highest degree is even. The end behavior acts like a parabola. So we had two even functions in our examples before. One was a positive x to the 4, one was a negative x to the 4. And we've already learned that a positive parabola opens up. So the end behavior of this one, can you see that your end behavior opens up? Of course, there's some woo in between here, just like last time. But can you see how the general shape is like a parabola? And same thing with D. D, your leading coefficient, is negative. So if you think of a negative parabola, it would open down, and sure enough, your end behavior acts like a parabola. So one of the first things that you're going to use in graphing these is a recognition of which one does it act like. Does it act like a line or a parabola? Is it even or odd? And what is that leading coefficient? If it's positive, then you think, well, how does a positive line act? If it's negative, how does a negative line act? The very first kind of odd degree function is a line. You've already done that like that. Lines act very much like lines. Makes sense? So if you have a positive leading coefficient, it goes up from left to right. A negative leading coefficient, down from left to right. You've done that before. We've done quadratics before. If you have a positive leading coefficient, it opens up. A negative leading coefficient, it opens down. But now when we get to the next ones, which are in the new ones, a cubic function, if it's positive, can you see how this is like a line going up from left to right? That you're starting from down here and ending up here. And when it's negative, so maybe right beside this, I'm just going to make a line with a positive slope. And beside this one, I'm going to make a line with a negative slope, so we can see that it's starting up here and ending down there. To the power 4, a quartic. These are going to act like parabolas. They're even functions. So if I think of a positive parabola, it would look like this. If I think of a negative parabola, it would look like this. And you can see that your end behavior matches. And finally, when we get to a quintic function, again, a positive leading coefficient will act like a line because it's odd. A negative one will act like a line with a negative slope, and we can see that our end behavior matches that. So it's just a start for us. It's a start to help us see which way that it goes. So you've drawn in those lines and those parabolas there. A few more definitions. And these definitions come up more often in calculus, and this is sort of where this is leading to, but we call certain points on graphs local maximums and local minimums. So on this graph here, it has 2 local maximums and 2 local minimums. So what happens is this guy here, right, that guy there lives in that town with the blue circle around it. And that guy at this little dot right there, he is the tallest person in his town. And so he's feeling really good because in his little town, he's the maximum. He's the most important, I guess in that town, height is important. And so he's the most important person in that town. And so we would say he's a local maximum because he's the big wig in his town. But here's another town over here, and there's another guy that's the tallest guy in that town, right? And he's the local maximum in his town. Now, if you compared the 2 towns, we would also call this guy over here an absolute maximum because he's the tallest in the whole thing. In this town, we got a guy that's the shortest. He's the local minimum. Nobody is shorter than him in his town. But he's not an absolute minimum because this graph goes on down forever. So when you get into calculus, these points become very important because maximums and minimums on graphs have huge importance, because if you have a graph that's looking at profit, and depending on your sales, you're making different profits and different costs, you want to find that maximum point because that represents when you're making the most profit. And so you would try to restructure your business so that you're working towards that goal of always having a maximum. Okay, you might have another function that is your costs. If you have a cost function, then those minimum points are really important because you want to find out what would we need to do to make sure that our cost is a minimum and figuring that out. So local minimums and local maximum points are very important for graphing. We're going to find out that with our skills right now, we have to use our graphing calculator often to find them. We won't know exactly where those local mins and local maximums are. When you get into calculus next year, calculus has a really nice way of finding those points. Okay, let's look at example example 1 here. And we're going to sketch a graph of each of these. Now, these are both graphs that you have never graphed before. So how do you sketch things that you've never graphed before? Draw a table of values, right? And that, you might even get some on your exam that you have supposedly graphed before because I've taught you them in this course, but you have supposedly forgotten. Okay? That happens, right? You go in to do a test and you're like, I don't remember how to do this. Well, you always have a table of values. So if you were in A here, wanting to know some points on your graph, you could plug some in. What are some easy values to calculate? 1. If you plug in 1, you're going to get -2. Other values that are easy. 0. That one's really easy, 0. So at this point, just start our graph off to the side. We've got 0, 0, and 1, -2. With that many points, do you feel confident you know what this graph looks like? No. This is part of the good. It's like, oh. This is part of the problem with a table of values is it takes a long time, right? You have to, let's put on some other points. Where would you like another point? 3? So you plug in 3, you're going to get 27 minus 27, you get 0 again. Okay. -3, -2. Plug in -2, you're going to get -8 minus 3 times 4, 12, -20. Okay, please correct me if I make any mental math errors. -2, -1, this is 3. Whoo. Okay? So now we've got a couple of points. We can also use our end behavior, because that's something that we've learned. What kind of function is this? It's an odd function, because the highest degree is odd. The leading coefficient is positive, so our end behavior is going to act like a line. So we know that it's got to start, I may as well start at this point down there. It has to end up here in order for the end behavior to act like a line. And so with the points that we have so far, this is what I know. Maybe something like this. You could use your graphing calculator to verify. We don't know that this is a minimum. We don't know whether or not it could have gone like this. That would still go through all of those same points and still have the same end behavior. So for our graphing right now, we're doing the best that we can. You're trying to draw a nice smooth curve through your points. But based on the points that we have and the end behavior that we know, both the purple and the green graph match. They fit through those points. They have the right end behavior. They would both be considered an okay sketch for this graph. Later on, we're going to figure out that the green graph is better than the purple graph, and why. But for now, there's our sketch. For our x to the 4 graph, table of values. What are some easy ones to calculate? 0. What do you get when you get 0? Positive 3. Perfect. What's another value that might be easy to calculate? -1 and 1. Of those two, which one do you like better? 1 is probably easier to start with, so we get -1 minus 6 minus 9 plus 3, -13. And if you plugged in -1, you'd get -1 plus 6 is 5 minus 9, -4 plus 3, -1. Okay? Table of values also gives you the opportunity to make lots of mental math errors. And I'm not saying that I did those quick. I hope that they're right. One thing you can do in your graphing calculator is if you type this into y equals, do you know where your table of values is in your graphing calculator? Yes? Good. So let's say we type something into our graphing calculator. I don't know if I want to type this all in. I'll do the first one. So we have x cubed minus 3x squared. Whoa. Thank you. X cubed minus 3x. Oh, should I try to make that same mistake 3 times? Would that be helpful? X cubed over minus, there we go, 3x squared. And if you hit graph, as I said, that matches up a lot better with the green one, although it dips down further than my green one did. Okay? And if you go second table, there's where a table of values is given to you. Okay? And if you move up and down, you can see, there I can see some of my negative values and some of my positive values. If ever you got bored in class and decided to go up and down for a very long time, which happened to one student, they say, "Hi, I got to 3 million," or something crazy. And then later they needed to get back to 0 and were frustrated with that. You can start it at whatever value you want by table set here. I didn't tell him that until he got to like 2 million. I'm like, okay, this is painful. Right now my table is starting at minus 3. If I wanted to start back at 0, I just have to push 0 there. I can make my table go up by 1s. I can make it go up by 2s. But now when I go back to table, it's starting at 0 again, which was nice for him after he was like, "This is so annoying. Push up and down forever." So on this one, we've got 0, 3. -1, -1, and 1, 13. Whew. So based on those points, do we have enough information for this graph? Yes. It is, for which one? 1, I get -1, -6, -7, -9, -16 plus 3, -13. Oh, yeah, like this should be down here. Yeah. Definitely. Okay. So now we've got points, and they're labeled mostly right. This is a negative x to the 4, so our end behavior acts like this. So we would need our graph to come down from here and end down here. So I'm going through my points. Woo! Maybe it looks something like that. And for this one, I'm almost certain that our graph isn't very good. But this is about all the information that we know for now. Now, we only use 3 points. We would get a more accurate graph if we added more points to our table of values. Okay? So, the ones we can do are 5, 6, and 8. But we're not going to spend too much time on those.